1, 2 minutes until...
Yeah, we're live now.
Okay.
Yeah. Good evening, everyone, and welcome to today's Morocco HPC webinar. I'm Safa, and I will be your moderator for this exciting session. Before we dive in, just a quick word about Morocco HPC. So we are actually a growing initiative that is dedicated to advancing high-performance computing in Morocco. We're trying to build a community of researchers, professionals, and students who are passionate about HPC, AI, and their real-world applications. And we try to do that through webinars, events, and collaborations because we want to start meaningful conversations and eventually push the boundaries of innovation. Tonight, we are very happy to continue that mission with a timely and forward-thinking session. Our guest is Mr. Soufiane Chami, Principal AI Solutions Engineer at SambaNova Systems. So he brings a unique mix of technical and strategic experience. So he helps lead AI adoption across Middle East and previously supported organizations across Europe and the region in scaling generative AI in an enterprise level. In this talk, titled AI Inference at Speed, how SambaNova is redefining sovereign AI infrastructure beyond GPUs. Soufiane will walk us through how SambaNova is rethinking AI infrastructure using their RDUs, which is a new architecture designed to move beyond GPU limitations and enable faster, more efficient, and sovereign AI systems. We will also be taking questions as we get them, so we want to have an interactive session. So please feel free to drop yours in the chat as we go. Thank you very much for joining us, and thank you so much, Mr. Soufiane, for accepting the invitation. And it's over to you now.
Thanks, Safa. Thanks, everyone, and it's a pleasure to get to know the Morocco HPC community, and also, I'm very excited for today's session. So in this session, what to expect is basically I'll try to give like an overview about SambaNova as another player in the semiconductors and also in the HPC market. So I'll tell you, for example, how we are doing our business, how our chips works, and the technology behind it, why we believe it's actually one of the alternative for GPUs in some, especially in the current AI workload and when in the age of agentic AI. So let's get started. Feel free to, as Safa said, post your comment, and I'll be happy to answer them in the middle of the presentation. So just a quick intro about SambaNova. So we are a company that was born in Stanford University by researcher in semiconductors. So their purpose was basically coming from the idea that GPUs are usually meant for graphic processing and not actually for AI. So we need to find a better way to basically run AI in a more efficient way, energy-wise, speed-wise, and also in capacity-wise. So we, like the company was founded in 2017, almost 7 years ago. And as I said, like started in Stanford University, it got backed up by Libotan, and he's very known in the semiconductor industry, not only in the US, but also worldwide. He's very, very well connected with TSMC in Taiwan and also other companies in China and also around the world. And he was like appointed as the CEO of Intel last month. And he's serving actually at the same time as our chairman and main sponsor and champion in the company. So 7 years ago, we got more than 1 billion in funding. And now we have team in Silicon Valley. We have team in Dallas and Stockholm. And also now we started our new team in Dubai and the Middle East. Okay. So this is just a quick overview about us. So the thing is, as I said, like one of the main challenges for GPUs, they are not actually built in the beginning for. They're built basically for video and graphic processing. They're not built to handle like tensors for AI and also the whole workflow of training neural network. It's not actually built for it. But the recent release of H100, A100 were actually really purposed for AI. But they still come with a lot of inefficiencies that we are going to present, and we're going to see how basically SambaNova is going to help. So we are like 5 nanometer for our like the level of precision of our chip. Um, One of the main differences between RDUs, we call them reconfigurable data flow units. So in GPUs, the one thing we do, the way how they execute programs is they are doing kernel by kernel execution. Meaning, I think in HPC jargon, it's like single instruction, multiple data. So you have like one instructions, one program, and you run it on a lot of data, and you run them in a parallel, and you go move to the next step. So it's a kernel by kernel execution. The way how SambaNova is doing it is actually multiple data, multiple instruction. So we have, what we do is we take the whole AI workflow and we map it on our chip, and then we run it with multiple data in parallel. And to do this, you need like a huge memory. And just to for the audience as well, the main challenge right now in AI is not actually the compute power; it's actually memory, because large language models, for example, are huge. And I think you've heard a lot about KV caching, for example. So whenever you are actually working on one of the layers on neural network, you have to, for example, in GPUs, you have to upload the data and upload the new weight to move to the next layer, and so on and so forth. And this is really, like, you see, and like there's a lot of inefficiency. You have to move the data, you have to get it back, you have to request the memory, etc. What happens with SambaNova is that we are relying on 3 level of memories, while GPUs are relying on like very small memory, on-chip memory, but also on external memory. So we have 3 memories. The SRAM, or what we call them on-chip memory, it's actually 500 megabytes. It's actually more than that, and we get to up to 5 gigabytes on-chip memory. And also the second tier is HBM, and the last one is high capacity memory. We're still upgrading. I think the last release right now, we got to even to 25 terabyte in the high capacity memory, and I think we got to 1 terabyte to HBM, and also to 5 gigabyte on the on-chip memory. What does that mean for HPC, and how does it contribute to basically to having a faster speed? I'll stop here because I don't want to talk a lot about it, but content. Let me tell you a lot of things about how this reflects in speed, how this reflects in energy consumption, and how this actually becoming very useful for AI. And then I can go back to this slide to tell you more about this into more details. Okay, let's skip this slide, and just to give you a little bit of benchmark. Right now, for example, we have a lot of players in the market. So we have companies who are specialized in optimizing running AI workload on GPUs. Their job is like, okay, I have an like DeepSeek, I want to run it on GPUs, but I want to run it on the maximum performance, which is basically the idea of HPC. We have like Hyperbolic, Fireworks, etc. But we also have non-GPU provider, and this is us, SambaNova, Cerebras, and Grok. So we are like basically 3 companies right now, plus 2 AMD, trying to run the AI at much faster speed. Right now, we were capable to run it twice as fast as GPUs for DeepSeek, but with one difference is that on SambaNova, we can run it on one node, but with GPUs, you need actually 40. This is the technical report for DeepSeek company. They said you need at least 40 nodes of GPUs, each 100, to be able to do it. So 1 to 40, this can tell you exactly already the difference in terms of performance. We have many other examples for Llama 4, which is the most recent model released by Meta. We got to 700 tokens per second, and this is just represent the speed of the generation of the word. Grok, our colleagues, they are also got to 600, but they are actually got challenged a little bit in the Llama 4, which is a bigger model. So the bigger the model, the more challenging it becomes to run it at a fast speed, and also to run it as with the efficient energy consumption. So, for example, for Llama 4 Maverick, which is a multimodal LLM, we got to almost 700. I think Grok, they got to 250. Of course, everyone you see here are actually GPU based, and they can actually get to more than 200. So we're talking here about at least 3 times to 4 times the speed. So why there is a need for speed? And this is really, really important to discuss. I think, and this is where it makes sense to discuss a little bit about the evolution of the AI since we heard about ChatGPT. So when we started hearing about ChatGPT, the first use case was this simple chatbot. So you just talk to a model, it reply back to you. That's it. Just one query, you get the answer. Now we've seen use cases where you upload your PDF and you just talk to your PDF. So this is like to be able to talk to knowledge assistant, you just talk to it once. It has to do one or two iterations and get back to you with an answer. But now we get to a much more complicated workflow. We started hearing about reasoning models like DeepSeek. We started hearing about like deep research, which is like a model. When you ask it a question, it tries to go through a series of chain of thought. It has to think more deeply to be able to come up to you with a very specific answer, a very accurate answer. And now we get to another wave, which is agentic workflow. So instead of one chatbot doing this chain of thought, we have multiple chatbots or multiple LMs talking to each other, thinking together to come back with one summarized answer. And when I'm saying thinking together, they can be doing some analysis, reasoning like math or coding. They can be consulting some data sources. Now, especially we are hearing about MCPs, which is another protocol to access to the data to actually enrich your response. So the problem is, as the complexity grows, so you, for example, let's say I want to ask an agent, what's basically the status of my inventory of this product? Okay, I'm a retail, let's say I'm Marjan or La Bilvi, and I want to know, for example, how much quantity I have for product X. So I have an agent who should go to the database, check it out, run SQL queries, another agent who should run the queries, the other agent who should get the results and analyze it, another agent who should. So we can see that there is a time here to communicate between all this. If we see that to get at least one agent to give a response, it's very slow, especially with GPUs. The tokens per second can be 20 tokens per second, 50 tokens per second. To be able to get the final response, maybe you have to wait for like 5 minutes or 1 minute. And as the complexity grow, the number of tokens required actually becomes more. This is where we need more, something much faster. So right now, the one of the solutions that's happening right now in the market is, as I told you, some companies that trying to optimize the GPUs, and this is basically purely HPC work. So you take the CODA, sometimes you even go to that level to be able to run basically much better scheduling, much better parallelism, etc. And you come up with a very efficient way of running those GPUs. For us, we don't have to do this because we come up with something much better about our architecture. As I promised, I will go back to my first slide to be able to talk to you about why this is actually more efficient. This is exactly the same idea. So with the complexity, let's say call center, you have to get one LLM talking to another, etc. With a series of communication before coming back to a question. This is where GPUs fails. When you have more than one calls, more than actually LLM talking to each other, especially if you have something relying on customer experience, the engagement will be very critical. So speed is very, very important. So right now, SambaNova, I'm sorry, the StreamYard is messing up with my slides, but so what we offer basically at SambaNova, and I can talk about this, it's not actually what I just want to say. If today developers want to get access to SambaNova, how they can get to it. So we have the because as you know, let's talk now HPC. For every semiconductor, for every chip, they have their own compiler language. So meaning that if you want to run anything, you have to basically run it at the low level in the compiler logic. Okay, so we have Intel, we have Coda, we have for example, Apple chips, etc. So each one of these, they have basically their own compiler language. Also, we have our own compiler called SambaFlow. And because the entry to market, we cannot not everyone is familiar with this. What we do is we offer like a full stack solution. So we give people the hardware, and on top of it, they have a software layer to basically manage the LLMs. And also we have the cloud, and which is I will show if someone want to try it out, we can show it. So this is a very quick comparison, and it's benchmarked by third party called Artificial Analysis. It becomes right now the industry standard for the benchmark on the, let's say, for example, when DeepSeek was released, the party was actually evaluating this is called Artificial Analysis. So for example, for Llama 2 1B, we can get with SambaNova 2,000 tokens per second. while with NVIDIA, you get only 300 tokens per second. And this means you can speed up the inference speed by actually more than 6 times or 8 times. You can even get to 20 times in some scenarios. And let me take a step back here. So, and I will allow myself, as I said, like to be a little bit more technical, more focused on HPC. So when we are talking about HPC, we're also talking about like the number of workers you need to be able to run certain jobs. Okay. And this also means the number of resources you need to run certain jobs. If you're doing geology discovery, image processing, maybe even deep learning training, etc. The speed, the time to get the final results really dependent on how many, how much capacity you have. Okay, so one of the things we focused at SambaNova is, again, we're going back to this first question: can we be more efficient than GPUs? Not only speed-wise, also energy consumption-wise, and also footprint, meaning how many hardwares you need to be able to get the job done. So one thing we were able to do is we were able to replace 10 times what GPU can do. When I say in GPUs, I'm talking about one node of H100. I think it has like 16 chips. So what 16 chips of GPUs H100 can do, we actually come up to do like 10 times more than that with only one node of 16 chips of RTU 40L. So this is basically what this slide is talking about. So in terms of memory, if let's say now you have Llama 4, or let's say you have Llama 70B, okay? If you want to get this running, you need at least one node of H100, okay? If you need to, and any company, they actually need more than that. They need actually Quinn, they need Llama 3, Llama 4, DeepSeek, all the variety of models. If you want to run another LLM, you need to bring another DGX H100, and so on and so forth. The thing is, with SambaNova, because we have 3-tier memory, again, which I will explain how they work, because of the giant memory we can hold to the compute node, we can actually host more than 100 LLM in one node. And this is actually much, much higher than what GPUs can do. I'm not saying GPUs are actually crap. I'm not saying this, because GPUs, I will talk about how they are useful for, and why, for example, they are still leading the markets. What I want to say is, the emerging markets and the focus of SambaNova is to how we can fill in the gaps where GPUs fail, and especially with the rise of LLMs and also Gen AI. So as I said, one node, we can do up to 2.6 trillion parameter. And this is why in one node we can hold DeepSeek, which is like only 500 billion parameters. So we can basically, technically, we can do five DeepSeek in one node. And yeah. Energy, which is very important. I think we heard some news about when the Blackwell GP200 was actually in the testing, and NVIDIA was actually planning to release it, and they delayed, postponed their release, because when they were testing Blackwell, it actually, the metal melt because of the heat. So they have to stop and do some testing and improvement. And it's not only that, it actually has to be water cold. And right now, GPUs, like NVIDIA is asking companies to build power plant to be able to power those things, like really, really crazy energy. With the same capacity, let's say, for example, like GB200 or H100, they require 40, GB200 like 140, 120, okay? We also, like SambaNova, we can do only 10, 12 on average. And energy consumption is really important. This is why we have to think about the total cost to own, like how much hardware you need, how much energy you need, how many talents, technical talents you need to operate in order to get to a certain level of performance. Okay, we can do all of this. We can consume, we can like multiply the memory capacity, the energy consumption, the speed with only one node, and actually we can do much more than that. Okay. So efficient token means like how much energy you need to be able to generate one token. And this is what we start talking about, like tokenomics, and how much does it cost you to generate one token. And this is where it's super, super important. I want to bring like other colleagues who are actually operating the same field. And to be able, for example, to do Grok, you need at least 9 racks. 9 racks to run Llama 70B at the speed of 500 tokens per second. For Cerebras, you need to do at least like 4 racks to be able to do that. For SambaNova, we manage it with like, it's effortless. We can do like Llama 70B at 500 tokens per second with only one node and 10 kilowatts. Energy consumption is very important for data centers and also for HPC because what does energy consumptions mean from HPC perspective? It means how many times you have to do data and memory access and movement. So the more you move your data, the more energy it takes for you to get it done. And this is why GPUs, like, they're having a hard time to optimize the energy because they are relying on external hierarchical memory system. So meaning that every time GPUs they want to run like process something, they have to offload the data they have right now and go and access memory, like request memory from the memory system and bring it back. So the movement here requires you more energy and more heat, etc. And this is where the efficiency is coming on. Because SambaNova have higher memory, we have 3 memories, and we are able to hold much bigger data than NVIDIA, for example. And this is where it's like for inference workload, we call it KV caching, for example. We can hold much more KV cache, much bigger than NVIDIA. So the movement to request the data, it's way less. And this actually means that we consume a lot of like way less energy than others. I want to stop. Do you have any questions, or I should just move on, continue? I don't hear you very quickly.
I said we can maybe just continue and then we can have questions at the end.
Yes, sure. So yeah, this is also another problem. So because the memory is very critical, so how the amount of data you can hold on the chip is very important to decide how big, how powerful you are to host one LLM model, like DeepSeek, a very big one, in one node. And this is where like one of the benchmark for HPC hardware to be able to reflect the memory and efficiency. Okay, I don't want to tokens per second. This is just an example how much tokens you can generate using GPUs H200 compared to SN40, which is like the 4th generation we came to. Soon we will release our 5th generation, and we can do this like very, very efficiently. Yeah, so this is very important, and it's very known for ML engineers. The composition of experts. You remember when I told you when the LLM or the agentic AI become a thing right now. So we need to have the capacity to speak to multiple LLMs and have them talking to each other before we come up to an answer. So the thing is, and this means, for example, you need to bundle, like have a collection of LLMs at one and call them composition of expert, and they call them like a COE. Most of the hardware, they cannot hold this much of memory and LLMs in one place. SambaNova was actually managing to be able to hold everything in one node. So one node can host multiple LLMs and expose them as one endpoint, okay, as one LLM. So when you send your query, there is a router, and that router think, okay, which expert I should talk to, and just route your query to the right LLM, and have them all together having at the same time. And this is induce like a very important metric, which called switch time, model switching time. So let's say you have like a GPU, you can run multiple LLM at the same time, okay? But the problem is, if you want to switch from one model to another, there is a delay because you have to offload the data, etc. This basically, you need to switch from one model to another and bring the other model up. For us, while it takes for GPUs like a few seconds, it takes us like a very, very small amount of milliseconds. It's almost our users don't even think about it. And yeah, so this is a recap that how is it different. And I want to go back to and I explained some part of it, but I want to go back to the first, and this will be my last slide. Is there a way I can skip much quickly? Just go back to our slides where I said how different our RDUs compared to NVIDIA, and why it's very important. How does that help for having like much faster execution, much faster inference than others? So yeah, so the thing is, as I told you, we have actually, instead of one memory for GPUs that has actually a hierarchical memory system, we have actually one memory on the chip, which is up to 8 gigabyte on-chip memory SRAM, and then just next to it is 1 terabyte of HBM, and just next to it is 24 terabyte of DDR. Okay, how does that work? So it's like, for example, if you are doing a recipe like making a pizza, so you have some ingredients you need right now. Okay, or maybe a restaurant. Let's say a restaurant. So you have some ingredients you need to have with you in the kitchen immediately. Okay, you need immediate access. This is on-chip memory. Some of them you have them in the storage, but they're still in the kitchen. This is HBM. But some other ingredient you have to go to the storage outside to get the ingredients. For NVIDIA, they have everything in the external storage. This is why execution takes a long time. For SambaNova, we can hold a lot of data in proximity, and we can minimize the movement of the data. And this is why we can optimize the speed, we can optimize the energy consumption, and also because we have large memory, we can also optimize the footprint. So yeah, thank you very much. I'll stop here. If anyone have any questions, but I think this is it.
Yeah, thank you very much, Mr. Sufyan, for this presentation. I think you mentioned that you were going to talk about how to get our hands on.
Yes, we
Yeah.
can do it. Yes, sure. So one of the things I promised as well is to do a demo. So I will show you I spoke about all these things in speed, etc. So let's see. Actually, I can do 2 demos. One is basically pure inference, and also one is, when I told you when you send a query and you need like multiple agents to plan things and to talk to each other. So let's get it done. Okay, so we can remove from stage, right? Or you want to remove the slides, and I can share my screen?
Yeah, I can remove them.
Yeah, by the way, I will share the link right now, and everyone can basically just log in and try it out. Can you see my screen?
I'm gonna add it to the stage. Like this?
Yeah, I can basically share the whole website so you can see the link as well. 1 second. Yes. Can you see it now?
Yes.
Yeah. So basically, if you go to cloud.sambanova.ai, and I will share this with you, Safa. Let me just do this. I'll share it with you, and everyone basically can just go and sign it. So we have right now, as I told you,
Sufyan, we cannot see. We're seeing the StreamYard interface on your screen.
Do you see the window?
No, I still see the StreamYard interface.
Oh, okay. Okay. Let me stop sharing and I can share again. 1 second. Now?
I think it's loading, but same thing. It shows the...
Okay, let me try one more time. Can you see it now?
And still loading. I think, yeah, it should work.
Yeah. So basically, as I said, can you see now the playground?
Yes.
Okay. So the purpose for Samba Cloud is to give lower barrier to entry. So not everyone is capable to buy the hardware. This is only mostly for data centers and also for enterprises. But for developers, we need to allow them to get a sense of how fast our chips, and how they can even start building the their applications based on Samba Cloud. So here, for example, SambaNova is hosting only open source models. We have DeepSeek, for example. Let's take DeepSeek. So DeepSeek, for example, we can ask it, and you can see here, it's just super fast. If you check it with the official website of SambaNova of CBD DeepSeek, it's way faster than this one. So for example, we can get like this one, 800B. It's already like 1,000 tokens per second. I can try, even this one is even crazier. So this is really right. It's not actually cache the response, it's actually. And the last one, it was announced, which is Gwen. And this one as well is a reasoning model.
Yeah.
So yeah, it's so you can play around with it. I'll let you have fun with it. So this is one. How basically can use it is we have an API. So you can just go ahead and generate your API key, and here you can do it with it's very compatible with OpenAI. So you only need to change your API key, the base URL, and you can just run it exactly like you're doing with OpenAI. We have basically function call-ins. We have soon we'll have Whisper. I think it's already there, but we have Qwen Audio, and we have Maverick and DeepSeek v3, etc. The other one that I want to show you is the AI starter kit. So we have a couple of codes open sourced that I can show you on GitHub. It's very public. So you can just go ahead and see a lot of applications with SambaNova. You can see the code and you can try it out yourself, and it should get to work. The last one, which is very interesting, is, and yeah, before I do that, we have a documentation. It's fully documented. If you have any questions, you can basically just check it out here. And the last one is the agent. What I told you, it's actually a couple of agents and LLMs talking to each other. So for example, let me ask it a question here. Can you give me a detailed financial report on Tesla? Okay. I have to make sure my APIs are actually working, but should be good. So yeah, and anyone actually can. So you can see here, there is a planner. So the planner is going ahead, and here's like this chain of thought, basically.
Excuse me, are you working on a different window? Because
Yes.
I still,
Oh,
yeah,
okay,
I
okay.
still see them.
Can you see this one?
Yeah, this one is, yeah.
Let me try again. I'll just do a new chat. So I want to see you. I want you
Okay.
to see things from the beginning. So I have to stop this one. So I was asking it. Okay, I have to. Okay, so I want to ask it, give me a detailed financial report on Tesla. And by the way, this is just a demo. It's not actually a production grid, so I hope it doesn't break. But the idea is, the purpose for this is just to show the value of having something really fast. It's for demoing purpose, mostly. So yeah, let's see. So it will go and check on the internet and try to get you. Try it. Again, because I aborted this one, I have to delete it. Let me do this. Just one moment. Let's try again. If maybe it's something wrong with the API keys, so I have to check to change the sessions. It seems like working. You can see here.
Yeah.
So it's really going and searching for risk assessment for a lot of things. Let's say, what does it say? And you can see he's actually generating a lot of tokens. So it's thinking. Maybe I was not lucky this time. I have to reload. Okay, I don't think, but I will share the link and everyone can basically try it. But I don't think we were lucky this time.
That's
I think there's an issue with the API keys. We just have to check it out. But I think the idea here, GPUs, there are a lot of people actually trying to find a way how they can optimize GPUs and they can find a better way to run it. And this is one of the main works for HPC. So HPC is not only just about coding in CUDA, for example, scheduling tasks, etc., and optimizing GPUs, but also there is another lower level, which is a way how you can basically just manage the workflow of the data and run it much more efficiently. So yeah, I think yeah, that's actually it.
Yeah, that sounds amazing. We have actually a question. So, Sam is saying, "Thank you very much for this insightful presentation." And can you see the
Yeah,
questions?
I can see the question.
Okay,
So
we have a
I
question.
yeah, go ahead.
Yeah, we have a question from Intisar. Thank you, Intisar, for joining us. Thanks for the great webinar. So, how does the three-tier memory architecture boost RAG embedded performance in real-world use cases like aerospace field?
Yeah, very good
And
question.
this is
So
also,
yeah,
yeah,
go
that's
ahead.
also a question I was thinking about because I was thinking about different fields. For example, yeah, here aerospace, maybe other modeling problems or other yeah, prediction problems, something like that. How does that help with the inference mainly?
Yeah, so the idea is you can definitely run basically anything on our chip. You can do image processing, you can do anything. It's just because right now our strategy is to focus on the alien because it's really one of the best use cases for our chips, but you can do basically anything. For the question from Intisar, and it's actually a very good question. So how can, for example, 3D memory architecture boost rack embedded? I would say it's basically, for example, let's say Mistral 5. It's an embedded model, and one thing we do is we just give you like a faster embedding speed, basically, way faster than what you can do on NVIDIA and what you can do on this. But there is one thing here. So there's one way, like there is one thing which is like, okay, I have a data, I want to generate the embedding, okay, and there's another step where I have my embedded data. I want to get access to it much faster. So this is another workload. So in this case, we are talking about like vector database frameworks. It's like Qdrant, Chroma, Pinecone, etc. So this is basically a different workload, and we have like different framework and tools. This doesn't has nothing to do mostly with the hardware. It's more about how you can much more efficiently get access to the data. I know some people. I saw some use cases when we use Redis because it's way faster than any other of databases. But to your question, if you want to generate those embeddings, using like fast inference is like can help you to update it like way faster. And let me give you a very nice use case where speed here like is very important and can be very helpful for RAG. So let's say you have a RAG, and it's depending on a data that keep changing every time. Okay, so it's like let's say 100 gigabyte, 300 gigabyte, and you want to build a graph knowledge. And the graph knowledge is just taking every information, try to link it to everything else. So basically, notoriously, graph knowledge, they take so much time, like a lot of time to get built. To be able to update that data, it's going to take you so much time as well. And if you have like a faster way to run it, it just allow you to boost and keep your RAG embedded data much more updated and up to date as fast as you can. I tried it myself with Nebula Graph on GPUs. It takes ages to get it done. So this can be one way to boost the architecture, like boost the performance of RAGs that rely on knowledge graph, for example. I'm not sure if does that answer your question, Intisar, but I think this is how I see it.
Okay. Thank you. I don't know if the audience have any other questions. In the meantime, so for the cloud, so you said that the chips are basically for bigger enterprises, right? That are supposed to build.
We have actually a research program where any
Yeah.
researchers who want to run HPC jobs and want to use our compiler. So I will share the link with you. So it's hosted with one of so it's do you know Argonne National Lab? It's actually one of the biggest labs for energy and nuclear energy. So what they did is they bought our and we worked with them on this. So they took our hardware and they implemented and they did it as a grant for researchers. So anyone who want to run HPC jobs, they can just fill out the required application form, and they will be able to get access to our chips.
Okay, that sounds
So it's
good.
available for research as well.
Okay. Okay, that sounds good. I don't know if there are any other questions. Yeah, so Intisar understands. So she says, I
Yeah.
understand. Thank you very much for the clear explanation. All right. If we have no more questions from the audience, I think we will wrap up. So thank you so much again for joining us. And
Yeah.
the webinar will still be on YouTube, so you can expect some questions on your LinkedIn
Yeah, sure.
after
Anytime.
people go and watch our webinar. So thank you so much again for accepting the invitation. Thank you for this amazing presentation. And thank you very much for the audience. And we will see you in the next webinar.
Thank you so much. Thank you for having me. Good luck.
My pleasure. My pleasure.
Bye.
Bye.